Hello, everyone. Please let me know if you can hear me clearly. So I can proceed. Hello. Yeah. So, welcome to my session, an introduction to the inner workings of LLM Inference engines. My name is Habib Shokoju, and I currently work as a machine learning engineer at Autodesk Research. At work, I try to work on advancing generative modeling research and integrating that into Autodesk products. My personal interests revolve around building research and machine learning systems. So I try to find intersection between both and see how it can work. On Twitter, I'm at Axolt. I run a small blog where I tend to post every now and then, axolt.com. And I like listening and reading autobiographies and memoirs. So my current read is Long Walk to Freedom by Nelson Mandela. So the agenda, the problem, a solution and its problems, inference engine techniques, and the takeaways. Let's just get started. So the problem, how can we generate texts? So how do you generate articles, poems, codes, summaries, letters? Essentially, it feels like today everything can automatically be boiled down to a text generation problem. So if you want to generate images, for example, let's say some workflow, you can actually write code that Mermaid, for example, would render into an image. So lots of things now are how can we generate that text? How can we generate the code that renders what we need? And the solution we have now would be large language models through autoregressive decoding. So you have some platform, ChatGPT, Grok, and you type in your prompts. What happens behind the scenes essentially would be the prompt goes into the model and generates one token at a time. So it generates that token, one token, the first one, for example, that comes back in as an input and it generates the next one and it goes back and generates the next one until it gets to the end of the generation sequence. But it's problematic in many ways. It comes down to two things. First would be limited memory bandwidth, while the second would be massive compute operations. What do I mean by this? Imagine you have an NVIDIA H100 where the high bandwidth memory HBM is about 80 gigabytes, and SRAM includes the L2 cache, L1 cache, that it's about 50 megabytes and 256 kilobytes. But then imagine you have a model, the Gemma 7B. Gemma 7B model is not probably going to be considered a large model today, given the kind of models we have in production everywhere. But then it's still about 17 gigabytes in BrainFloat 16 precision. Now, if you have to look at 17 gigabytes and 80 gigabytes of memory, that's fine. But then the problem here is when you are running the compute doesn't run on the high bandwidth memory. It actually runs on the GPU cores. And those do not have so much. So imagine, let's say they have about 256 kilobytes to work with. How do you fit in 17 gigabytes into that kind of space? What will often happen is, based on whatever library and tooling you're using, it would copy each layer of your model onto the GPU cores and run whatever computation it needs. It does this for every layer, maybe not every layer, but hopefully the point is clear. But it does this for as many layers it can potentially work with or fit in. And this happens for every token it generates. So given that large language models have massive weights and there are multiple data movements of this kind, you can really see that the GPU would be staying idle most of the time because a lot of time is spent rather than on computation, it's spent on moving data from the high bandwidth memory into the SRAM and the cores for compute. So what do I mean by wasteful computation? I already mentioned that earlier, generating one token at a time. But then I could just show this via this quick animation here. It's my first time doing this, so I hope it goes well. When you are doing autoregressive decoding the naive way, you pass in your prompts, that goes into the model, that's fine, then generate the output. That then comes back in as the input, and all three tokens go into the model and generate one token. Not one, multiple, but we only use the last token here. Now, all of them come back into the model and are generated as outputs. If I'm to speed this up slightly, you'd see that it does this every single time until it's done generating. What will happen is, as you can see, when it's computing this, let's say it's the attention mechanism, where the last token would have to look at the tokens that have come before to see if they how they could influence its own representation. And then when you have the outputs, one other thing to notice here is, while it's generating multiple tokens, we only use the last one. So there's the first part where, even though this, let's say, Roses has already done compute attention mechanism on the one before it still has to do it when the last token here is being generated. That's one wasteful way to do it. Then the other part would be, all the tokens that are also being generated here are being discarded. That's not great either. I'm going to go into the inference engine techniques part here, which just simply boils down to, what are the various ways that LLM inference engines try to fix this potential issue. Not potential, but try to fix this issue. So, inference engine techniques. The first that I'll be looking at is KV caching. KV caching basically fixes the problem of, if we need to calculate attention for every new token, and it has to be done on all the tokens that have come before, can we simply cache that? Hence, it avoids redundant computation during text generation by storing and reusing the intermediate key and value attention vectors for tokens that have already been processed. The words key and value attention vectors do not exactly really need to be fully understood for the rest of the conversation. It's just machine learning buzzword, not buzzword, but machine learning jargon, to be precise. So let's see how KV caching works. I have an animation here as well. I'm going to slow that down. The first part would be, if you have a prompt and then you calculate attention on every single token backwards, as I said, you do that once in the preview stage, and you get the key value pairs I talked about earlier. So we have that stored in a cache. The good advantage to this is, while we are doing preview cache, we still get an output. So that's good. But what then happens is, only that generated token is then passed into the model going forwards. So every single thing that has been generated previously go into the cache. That's the key and value attention vectors. So when you are calculating attention mechanism, which is probably one of the most important parts of how language models work, you do not need to pass in every single token anymore. You only do the last token. This is why when you get to see some article or blog post saying, oh, we were able to speed things up, the KV cache is one way they probably have done to go about this. And this then happens for the following tokens. So you go in, generate the outputs, you add to the KV cache, so only the last token is required. This happens until the final token that needs to be generated. So that's essentially what the KV cache does. And this is going to keep on going till the very end. But hopefully the points passed across how this saves compute. And then imagine if at that point, let's say at this point where we are doing the bush, we have to compute attention for every single thing and passing all the tokens into the model. That's not very great. I'm going to be going to the next part of this talk. So KV cache only processes new tokens. All previous context is cached. I think that's kind of basic software engineering practice, right? But then it's not always so clear when there's something as new as language models. And then this is used in inference engines anyway. So KV cache enables stateful decoding, eliminates redundant computations, drastically reduces latency, and reduces memory bandwidth problems. But then the KV cache in its plain manner causes a lot of problems as well. Problems to the finish. So the first part would be that tensor libraries would like the data representation in memory to be contiguous. So let's say you have some array and it's this way 0, 1, 2, 3, 4. If you want to multiply every single thing here by 2, you probably only need to know the start of the array and every the number of items in that array. So let's say 5. Now you know where it starts, you know where it ends, you know how to compute on all the items between the starting point and the ending point. Now imagine if it's non-contiguous. How do you essentially go about this? It's going to be much more difficult to achieve this if it's non-contiguous. Hence, these libraries would often represent data in a contiguous manner. So if you have a matrix, it's 3 by 4. But what PyTorch essentially sees, for example, would be this in contiguous format. And it stores some metadata saying how it's going to go from one value to another as metadata. So let's say you want to go from one row to the other. It knows, oh, we need to skip 4 values to get to the next row. But if you want to get to the next column, you need to skip just go 1 value to get to the next one. So that's what would often happen behind the scenes. But then it's problematic. Why? It's because of memory fragmentation. So imagine you have this as your memory, and then you try to fit all of this in. It fits in properly, right? But it's not always the case that you would have a perfect scenario where you can fit in everything into memory this way. Imagine if you have this instead. Where did the blue items go? There's space for it, right? So there's space for this here, but it's impossible to fit it in because now it's fragmented. It can't fit into contiguous memory as you'd expect. So the plain KV caching leads to memory fragmentation. And just going to show that quickly here. So imagine you have in your KV cache memory, and then you have 3 requests, one that's dealing with 5 tokens, one dealing with 4 tokens, and 7 tokens. That's fine. That's good. But then the first request is completed. So now you have all of this space left. Then request B grows to 6 tokens, probably because you need to generate more text. But there's no space for 4 tokens to grow to 6. What will happen is it copies into a new location and it grows the tokens as required. But there's still a problem here because it's now fragmented. What then happens if you get a request with 7 tokens? You can't fit that into memory. But there's space, hence it's quite wasteful because it can't work anymore. So contiguous allocation leads to fragmentation. So the fix here would be PagedAttention, where PagedAttention treats the KV cache like virtual memory. It essentially gives an illusion that you have contiguous blocks logically, but behind the scenes, it's storing things in a non-contiguous manner on actual memory. So this makes life easy for the tensor processing libraries because they're actually seeing contiguous memory in the blocks they are being presented. But behind the scenes, that's not exactly the case. So what do I mean by PagedAttention? So let's say you have a page table where each table is representing 4 tokens. So you have P0 to P5 here, but there are about 4 spaces in it if you think of it that way. So you have your first request here dealing with 5 tokens. This takes 2 pages of memory. But then because it's dealing with pages, it's actually taking 8 here because you can't like share pages between multiple requests in this setup. So you have your new request 4 tokens, 1 page is fine. A new request comes in 7 tokens, that's also fine. So if you have to see here in the page table, everything is actually contiguous, so it's not much of a problem. And then you have what the tensor library is saying. P0, P1, that's contiguous. P2 is contiguous. P3, P4 is contiguous. So what then happens is if you get request B now growing from 4 to 6 tokens, you no longer need to copy the data from one block or from one part of memory into some other part just so you can fulfill the contiguous memory requirements. You just need to allocate a separate page which would contain the data you want. But then in the page table, it's set up so the tensor library is actually not exactly saying that in physical memory, it's not contiguous. All it can say is this: there's P2, there's P0, P2 comes before P0, and that's all it needs to know. Hence, there's no copying, and your pages can be anywhere. So when you have a new request with 7 tokens, you can simply place it anywhere you want, P5, P1, and that's just fine. No memory wastage. Now, paging doesn't exactly eliminate the problem. It just ensures that it doesn't happen as frequently as it would be without fragmentation. Now, the block size is something you can configure on inference engines, and like that comes down to what the use cases would be for each person. So PagedAttention solves internal fragmentation, enables efficient memory sharing, and improves GPU utilization. The third part I'll be looking at will be prefix caching. Now, prefix caching essentially says if you have 3 requests coming in, 3 requests, 4 requests, whatever, more than 1 request essentially, and each request share at the prefix the same part of the prompt, is there a way in which you do not need to recompute the KV cache for every single one, provided given that they are sharing that part of the prefix? Hence, it reuses the KV cache of the shared initial part of the prompt, that's the prefix, as I said, across multiple different requests. So look at this. Let's say this is via VLLM, which is one of my favorites, and you have 4 prompts, which says the quick brown fox now jumps over the lazy dog, the quick brown fox now jumps over the sleeping cat, and so on and so forth. The first 2 are sharing the same prefix up until this point. The third one here is only sharing parts. The last one is not sharing any. But then if you imagine that we have the tokens here, which essentially saying would be the word count. It's what doesn't exactly translate directly to tokens, but it just helps with the analysis or analogy rather. So let's say we have about 4 tokens per page. What will essentially happen, you see here. So you have your page table once again, and your first token comes in with 12 your first request comes in with 12 tokens, where if one page is taking 4 tokens once again, that essentially means 3 pages. But then because request B is sharing the first parts of its own prompts, you can essentially hash the contents of those tokens and then find in cache what the KV cache values are. Essentially, we see that the first 2 pages have been referenced by request A and request B. That's reference county of 2, reference county of 2. The remaining parts of the request or the tokens can then be filled into memory. So A and B share 2 pages. Request C shares only 1. So P of P0 here is only being referenced by 3. P1 is being referenced by only 2. Request C shares only 1 page, while request D with 16 tokens picks up the rest. Hence, the important part here is we do not need to compute the KV cache for those prefix anymore, and then now you just simply referencing from the KV cache. This ensures you don't have to run compute for those, and it makes it much faster. You don't have to do the data copying thing between high bandwidth memory and the cores anyway. So that's good. Request D has a unique prefix, so it's taking up the rest. So prefix caching, memory sharing, memory plus compute savings on shared pages. Prefix caching pre-computes the shared prompts, drastically reduces the time to first token. So if you have a case where you're passing in, let's say 5 different requests, 5 different prompts, and the first one is having its prompts being shared by the rest, the remaining requests would essentially get their first token much faster. That's what's meant here by drastically reduces time to first token, because you're not computing for them anymore, and it saves significant compute. So continuous batching. Continuous batching maximizes GPU efficiency by treating text generation as a continuous dynamic process rather than a series of rigid static batches. What this essentially means is when you want to do a batch request into a neural network, you'd often create this large matrix where each row references the request you're working with, and all of that go into the model at once. The problem here though is, as you see here with static batching, imagine we have a batch size of 3 and we have multiple requests, about 7 requests here. The problem here is if the first 3 are done, because we are creating this static matrix where everything is going into the model, the uh, the first request is still part of that batch. It's still taking up space and it's idle. Hence, the remaining requests are still waiting because we've created this matrix where each request is essentially tied to the batch it is working with. So every single thing here has to wait until the longest token in that batch is done, until the longest request in that batch is done generating. Uh, but then if you have continuous batching where the concept of batching is taken away from the request and you just have like this level of abstraction where each request can simply come into space, and if the first batch is done, that request is freed up and something else can come in and keeps processing. So imagine you have something like this. Now you have a batch slot 1 to n, depending on how much memory you have to work with. Now, we do not have, as in the case with static batching, you do not have 4 requests waiting anymore. You only have 2 because there's no space anymore on memory. But then slots 1 and 2 are being taken up by request D and request C as soon as there's available space on memory. So that's essentially what continuous batching is. And this works because now with the KV cache, we've isolated the prefill stage from the decoding stage. Hence, every single time, because we are only passing in 1 token, all the tokens here can actually be batched now at that regular static batching level, and you can generate tokens there. So it's still 1 token, even when this is request C at token 4 stage, token 1 stage can still work. So that's essentially what continuous batching is doing. It decouples batching from sequence length, maximizes throughput, and then reduces average latency. I think this is the final part. Speculative decoding. Speculative decoding essentially comes down to 1 or 2 main concepts, which is you have your large language model. It takes quite some time to generate your token from your large language model. But imagine if you have a smaller model, and this smaller model can still work fine and can still generate tokens for you. So yes, it might be wrong. I don't know if some of you have played with models that are like quite small. Yeah, sometimes it generates useful things, but it can hallucinate and say rubbish quite often. But the larger ones tend to be much effective. So what speculative decoding does is it uses this small fast draft model to predict several tokens in advance, then has the large powerful model verify all of them in a single step. What do I mean by this? There's another animation to go with it. So you have step 1, your draft model and your target model, which is the large one. You do your prefill KV cache stage. Then for your draft model, you get your token. I think I should just slow this down slightly. Now your draft model comes to generate multiple tokens. Now this is something you can configure with an inference engine. You can say, oh, for speculative decoding, I want to have a draft size of 5 tokens, 4 tokens, depending on how much you would like to work with. And this generates multiple tokens. I think this is going to be like 3, 4. It generates 4 tokens. Now, all of these 4 tokens then go into the verification phase, with the large language model. Now, at this point, it's similar to when you're doing your preview phase, as shown in the previous slides. Calculate your attention, and all of these tokens then go into the target model, and this generates all those tokens. Now, the point here is the fact that the draft model got all these tokens right is a good thing, because one, you are using a smaller model and you're able to generate your outputs much quickly than if you had to use the large language model to do this. And two, the large language model can verify every single thing in that one swoop. So you are not doing it one by one. Hence, it's saving computation in the sense that it's much cheaper to do all of that generation with the draft model, but for the large model where it's much more expensive, you are doing it in one pass, in one forward pass, not multiple. What then happens is it looks at the outputs for every single token generated here and see if it aligns. So, for example, this output here from the draft model aligns with birds, which the large model would generate usually. Then the next one, width from the draft model aligns with this, which the large model is giving us. This one also one aligns with what the large model is saying. But then at this point, the large model is saying stone should be the next token, not gun. Hence, it discards the token gun and then goes with stone. So if, for example, we use a model that's like quite silly, not effective, and it generates gibberish for the 5 tokens, if it's basically not getting the next token correctly, then now the optimization you're looking to get kind of backfires, because you spend time generating with this draft model, but then the large model is saying no, that's not correct. But on the good side, if the draft model is actually doing a good job, the large model doesn't have to do so much work anymore. That's essentially what speculative decoding is. Using a draft model to speculate what the next couple of tokens would be, then the large model is verifying that this is actually correct. Hence, speculative decoding maintains output quality of the large models. It breaks the one token at a time bottleneck, lowers perceived latency. So, just to go over the techniques I covered. First is KV caching, which stores and reuses the key and value tensors from previous calculations. PagedAttention, which decides the KV cache, which divides the KV cache into smaller blocks to be accessed via a page table. Prefix caching, which stores the KV cache for common initial sequences, that's from your prompt. Continuous batching, which processes incoming requests as a continuous stream, dynamically creating batches. And speculative decoding, which uses a smaller, faster draft model to generate several tokens at once. What now? What's the point of all this? The first part would be you can use this in your favorite engines, VLLM, for example. And in the case of VLLM, the KV caching, PagedAttention, and continuous batching are all available out of the box. You can use prefix caching as well by simply just passing in the arguments. And then you can also use speculative decoding. Hence, if you are having like some offline generation use case, and then you've been thinking, oh, how can I make this much more optimal? Chances are the approach you're thinking of has already been covered by the inference engine you are working with, or there is an inference engine that already does whatever optimization you are looking to implement, and it's just left to you to decide if you choose to go with that or not. The other part is you have a better understanding of how it works behind the scenes. So thank you. I don't know if there are any questions. The slides are available in this link. For the animations, you can find the code used to generate them in this link as well. I did not exactly write them by hand. It was a large language model generating them for me once again. Thank you.
All right. Thank you so much, Habib. There's currently no question. Does anyone have a question you can ask in the Q&A tab? Um, okay. No question. Okay, I think you can maybe go ahead to give closing remarks or something, and then we can end this session.
Okay. Just going to say, if you have any questions outside of this, you can always reach out to me on Twitter. My email is not here, but I think it's going to be somewhere on that web page there. And then if you are probably doing some large batch generations, you can do this with whatever inference engines. I'd recommend VLLM. There's OLAM as well. I think that's also a good way to go about it. So I think that's about it. That's all I was looking to share. Thank you.
All right. Thank you so much, everyone. That's the end of this session. The next session will start in about 10 minutes. So you can hang around till the start of the next set of sessions. Thank you.